Hi, this is Ms. Fitzmaurice. This video is an explanation of her response number 3 in your review packet. So, in this problem, and by the way, the background noise is the Copenhagen airport. In this problem, we have two springs. We're dropping two blocks on the springs, and one is sliding down and hitting the spring, and the other is just being dropped straight on the spring, and we want to know which spring will be compressed the most. So, we can use conservation of energy to analyze both of these situations. So, in test 1, if we want to know about the compression of the spring, we can write out spring potential energy at the end, and we see that at the beginning it's just at some height. For the sake of this problem, I'm going to call it h. So we have us is equal to ug. And what that means is 1/2 k delta x squared, and this delta x is what we care about, is equal to mgh. We can do a little bit of algebra, and we can solve for delta x. So I'm going to do that right now. I'm multiplying both sides by 2. So I have 2 mgh. I'm going to divide both sides by k. So the 2 over here goes away, the k here goes away. And then I have x squared, so I'm going to take the square root. And I have delta x is equal to square root 2 mgh. In trial 2, so this was trial 1, in trial 2 we're just dropping the block. Okay, and assuming the spring isn't squished all the way down, it also starts out with gravitational potential energy at the beginning, ug, and then it ends up, at the end it has both, the spring is going to be stretched down, so I'll draw the end piece here. The spring is stretched down, so there's us, but it actually still has some final ug. Okay, so if they both start out with the initial height h, then that means at the beginning, okay, I'm using sigma e naught equals sigma e. At the beginning I have ug, and it's just mgh. And at the end, maybe let's call this h1. I have height mgh1 because my object is still at a height, plus 1/2 k delta x squared. And again, I can do some algebra to solve for delta x. So I can subtract mgh1 from both sides, so I have mgh minus mgh1. I can equals 1/2 k delta x squared. I'm going to factor out the mg's, and so I have mg h minus h1. Again, I'm going to multiply both sides by 2, so this 2 right here will go away, and I'm going to divide both sides by k. And then finally I am still left with x squared, so I'm going to take the square root. So I have delta x is really almost the same thing. The only difference is these h's. And we can see that h without h1 subtracted off is going to be bigger. So that means delta x is bigger in case 1. Whereas h minus h1, whatever h1 is, h minus h1 is smaller than h, so my delta x has to be smaller. Alright, so that's how we explain it in equations. Your job, however, was to explain it into words. So I'm going to go over the points you get along the way in your explanation. Alright, so you get 1 point for stating the correct answer, that delta x is larger, or the compression is larger in case 1. You get 1 point for stating that energy is conserved in both cases. Okay, but you have to write this out in a sentence. You get 1 point for explaining that in trial 1, the object has UG at the beginning and US at the end. So you're sort of saying, for trial 1, and you're stating this in words, UG at the beginning is equal to US at the end. So a correct conservation of energy statement. You get 1 point for solving. This doesn't quite have to be in words. You get 1 point for stating that in trial 2, you have UG at the beginning, and at the end you have UG and US. Okay. You get 1 point for saying that you have assumed the spring is not totally compressed.
Personmeddelelse til passagererne Elise Bensen og Thomas Lagerrejsende på SAS-rute 1872 til Stavanger. Venligst til afkommende kontakt udgang nummer B8 gaten lukker.
And you get 1 point again for solving the second time that delta x2 is equal to the square root of 2mg h minus h1. Alright, so what I need you to do now is take your paper. You're going to use these points to rewrite your answer. It should still be in a complete, coherent paragraph. And then to reflect.